Thank you very much, Luis, for the introduction, and I would like to thank Andreas and Nilangelo and all the other organizers for accepting this contribution as a talk here to Beyond I.I.D. It's a great pleasure for me to be here. I'm sorry that I couldn't stay for the whole conference because of some works at home that demand my attention. But yes, it's a particular pleasure for me to come back here and talk about something Gaussian, continuous variables. It's not the typical topic that you get at this kind of conferences, which is more information theoretic, but it is nice for me because I was in Cambridge in the final year of my PhD about 13 years ago, and at the time I was doing everything Gaussian. I didn't know anything about all that we are studying now, information theory, resource theory, and so on. So what we are looking at here are very old questions, which somehow settle the score of doubts and I would say investigations that part of the community working in continuous variable systems has been looking at for many years, but that at the time we didn't have the right tools to solve these questions in general. So now what we're going to do is try to assess in a very general term what is the ultimate power of the toolbox of Gaussian states and Gaussian operations for quantum information, quantum technology with continuous variable systems. So for those who are not familiar, when we talk about continuous variable systems, we are talking about information encoded in degrees of freedom which have a continuous spectrum. So instead of talking about a qubit, which if you measure in any basis, then you can find just two possible outcomes, then you can think of, say, variables like position and momentum. And if you measure that, then you can get as an outcome a continuum of results. So you can encode information in these variables, and this can be realized with light, we will see, with many different systems. And it's a kind of analog technology as compared to the digital one, which is the one based on qubits. And within this approach, a lot has been done experimentally and theoretically, focusing on specific classes of states, which are called Gaussian states, for reasons that will become clear, and operations that preserve Gaussianity. So it's a special class of states in an infinite dimensional space that are easy to prepare, easy to study, and they are quite good for many applications, but their power is limited. So using the tools of resource theories here, we would like to give an answer to how limited is their power and what do we need to do in order to go beyond. So as we were I was noticing from the program, today seems to be the day of resource theory. So we already seen something from Iman Marvian's talk in the context of thermodynamics, and then I will use again this approach of resource theories for studying state transformation but in continuous variable systems. So what are resource theories? Just a little bit of tiny introduction in a nutshell for students that maybe are not familiar with them. So it's a mathematical framework that allows us to treat on a very general and kind of unified approach concepts which are believed to be useful for something. So a resource is something that allows you to do a task that otherwise you couldn't do or you couldn't do as efficiently. And once you characterize your particular resource from the framework of resource theories, then you can go and address some questions that are recurrent and independent of the specifics of the resource. And in particular, we care about quantum resource theory. So our resources have to be phenomena that are incompatible with the classical description, such as superposition, like coherence or entanglement, and so on. And the idea is the following. We have a very nice review which came out just last month, so go in there if you want to see more. We also have a review on the specific of resource theory of coherence, and there's more reviews on different resource theories. But in general, the idea, and this is not even as general as it's possible, because here we're talking about resources as quantities that can be measured on states, okay? So suppose we have a set of states, quantum states, then we can identify a subset of these states which are cheap. So they are given for free. So these states, they do not contain any resource. So if you think about entanglement theory, this set of free states would be separable states, okay? States that are not entangled. And these states you can always obtain. You can imagine that they are easy to get. Of course, it depends on the specific resource. All the other states, they contain some amount of resource, so they are resources. And so you're classifying states in this way, free versus non-free. On the other hand, you can also classify operations. So there are free operations and there are non-free operations. So non-free operations are operations that you're restricted. You cannot implement unless you consume some resource. While free operations are operations that you can implement for free, but if you use them, you can only create free states from free states. So the idea is the following: if you want to look at manipulation between states with different types of operations, if you're only given a free operation, again, in the case of entanglement, this would be local operations and classical communication. So if you're only given free operations and you apply them to a free state, then you get back a free state. You can't create anything which is non-free with a free operation. And the idea is that normally these free operations, they describe the restrictions that you have in your physical theory. So again, for entanglement, we have a very clear paradigm of two separated observers, and I can do local operations there, the other can do local operations on the other side, and then we can do classical communication. So this is where the paradigm of the operations comes from. And if you want to do something more, then you have to invest in resources. So if I apply a free operation to a state which has already some resource, I can convert it to another resourceful state, but I can't increase the amount of resource in the state. So for this we require a proper quantifier, but the idea is that you can go from this to this by free operations. Your resource content can stay constant or go down. Sometimes it goes down, and so you go from a state with a resource, wasting it, back down to the set of free states. The only chance you have in order to create a resourceful state from a free state has to be by implementing a non-free operation. And similarly, the implementation of a non-free operation requires you to invest in the use of some resource. So I was saying this is very general and abstract, and then there are specific cases which are well framed in this perspective. So for instance, the one that I was mentioning a lot, because it's been the one that most of us studied so far, is entanglement theory, where free states are separable and free operations, because of the physical paradigm, are LOCC. Now this is not the largest possible set of operations that preserve free states, but are the ones that represent the physical situation at hand. There is another type of correlations, again in bipartite systems, called steering. So this is something which is in between entanglement and Bell non-locality. It's an asymmetric form of non-locality, which means that your state is incompatible with the model that assumes a local hidden variable on one side and a local hidden state on the other side. While for entanglement you assume a local hidden state here and there, and for non-locality you assume a local hidden variable here and there. Steering is in between. And if you have states which are steerable, they are not only entangled, but you can also verify their entanglement without assumption on one side. So the free operations in this case are one-way local operations in classical communication. And of course states which are not steerable, they may be separable or even entangled but not steerable, so this would be the free state. Then other resources, for instance coherence, we have seen in the previous talk. Free states are just diagonal in a fixed basis, and then there are various types of incoherent operations that preserve these diagonal states. You can have the analogous notion in continuous variables, and this is sometimes called non-classicality. And there usually you take as your reference, this is very unfortunate terminology, but you take as your reference basis the basis of coherent states, which actually would take the role of incoherent, but it's the optical coherent states defined by Glauber. And so if you have mixtures of optical coherent states, these are considered classical. They are compatible with the semi-classical description of light. And operations that preserve these mixtures are passive operations, so they do not create energy. And the other resource that also Iman mentioned is the resource theory of thermodynamics, where if a state is in thermal equilibrium, then it's for free, and to bring it out of thermal equilibrium, then you need to implement some operation that is not preserving the energy. So thermal operations are your free operations, Gibbs states are the free states, and being out of thermal equilibrium is your actual resource. So these are just some of the examples. Now each of those theories then maybe can be treated a bit differently, but you can ask the similar questions in all cases. Questions like, what are the conditions such that I can transform state A into state B under free operations only? So sometimes this is possible, some other times this is not possible. I already told you I can't go from a state with less resource to a state with more resource just by free operations if it's one-to-one copy, so beyond I.I.D, let's say. But in other cases we can. If we can, then how efficiently we can do it? Typically you quantify these things looking at the rates. Okay, so suppose I have n copies of my state, I want to convert it into m copies of the other state, where I factorize m as nr. What is the optimal rate of this conversion, such that this thing can be done perfectly in the limit? That's I.I.D setting. This remainder term has to vanish. So this rate is the maximum overall chosen set of free operations. Usually you look at these things when you want to consider also particular cases like distillation, dilution, but state transformation in general. And then how do we quantify resource content? What are monotones which are compatible with resource theory and so on? And answers are different in different cases, but there are few results which are kind of universal. So one of these nice results which is kind of universal is the characterization of resource theories which are eventually reversible. So this result is due to Fernando Brandao and Gilad Gur, and there were some previous inputs also in other papers by Oppenheim and Diarodetsky in the context of thermodynamics. And what they studied a particular class of resource theories such that they can provide very general conclusions. The idea is, first of all, here I'm not going to be extremely technical, but so they consider, again, this is not exactly precise, so but they consider the maximal set of free operations, which means I take the largest possible set of operations that maps my free states into my free states. For entanglement, this is larger than LOCC, larger than separable operations, and it's separability preserving operations. But actually in their paper, if you read them, there's some notion of epsilon separability preserving operations. It's a bit more complicated. But the idea, you think about the set of the largest possible set that preserves free states. And then you have to put some assumptions on the structure of the set of free states. And some of them are very natural. So if I have my states and then I take tensor product of them, then I keep getting a free state. So it's closed under tensor product, closed under discarding subsystems or partial traces, closed under reordering permutations of subsystems. This is important, topologically closed. So if I have a sequence of free states and they converge to another state in a certain norm, then this limiting state is also a free state. Okay? And crucial thing, the set of free states is convex. Okay? Which is all the case in all the examples that I mentioned before. So if you take all the maximal set operations and you take a convex set with these extra assumptions, what they showed is that independently of the specifics of the resource, any resource theory with this structure is asymptotically reversible, which means that the rate of converting a state into another is just the inverse of the rate of converting the final state into the initial one. A little bit like what Iman showed before. Okay, so any resource theory with this maximal set suitably defined and suitably defined convex set of free states is maximally asymptotically reversible. And in particular, this means that if you have a resource theory where you consider distillation and dilution, these rates of distillation and dilution are the same. So distillable resource and resource cost are the same, and they converge to regularize relative entropy of the resource. Okay? And this was already studied in the case of entanglement theory in a previous paper, but this is now the generalization to any resource theory. So it's a very nice axiomatic approach. And I have to say there are also some cases of resources which we know, which are even better behaved than the general case, because you can even have cases in which your set of operations is not the maximal set, and still your resource theory becomes asymptotically reversible. This is the case for coherence theory under a set called dephasing covariant operations that was studied by Iman Marvion and Speckens, and also by Chidambar and Gur. And if you've been to Bartos Regulus poster yesterday, you could have already learned this result yesterday. Okay, all this is nice for finite dimension, and this seems very general and powerful result. What happens when we move to infinite dimension? Okay, so we want to answer this question for continuous variable systems, and we want to do that in particular focusing on Gaussian states and Gaussian operations. On one hand, because that's the only thing we can do. It's too hard to consider arbitrary infinite dimensional systems. On the second hand, because they are very relevant physical resources. So the idea is, if you have a collection of, think of light, the electromagnetic field, quantized, it's just a collection of harmonic oscillators. Each of these is called a mode of the field with different frequencies. And now, every time you consider the ground state of a collection of harmonic oscillators, or just the thermal equilibrium states, these states are Gaussian states. And if you consider any other Hamiltonian and you make this kind of approximation of small oscillations, say the harmonic approximation, then you have again a structure where ground state and thermal equilibrium states are Gaussian states. So they are relevant because they enter in any physical system under specific regimes, and in experimental implementations using quantum optics, vibrational modes in trapped ions, collective spin components of cold atoms, optomechanics, they are just the natural, the coupling between these systems is naturally quadratic, and so you have naturally Gaussian states coming into the picture. You can implement them controllably in many different systems. And from the point of view of mathematics, they're easy, because despite living in infinite dimensions, they are specified by a finite number of degrees of freedom. So we can actually do things with them. And they assume a very nice geometric structure, which comes from moving into phase space and using techniques from symplectic geometry. So technically speaking, if I have to define it mathematically, I would say the Gaussian state is a state of a collection of n harmonic oscillators such that in phase space it can be described by a Wigner quasi-probability distribution which takes the form of a multivariate Gaussian. So it's entirely specified by one vector of first moments, which is this d, and then one matrix of second moments, which is this v. So here we're talking about all these oscillators. Imagine on each of them you have defined position momentum of quadrature operators. For light it will be, say, intensity and phase quadratures and so on. And then the first moments is just the expectation value of each of these. Okay? And so you can imagine first moments just tell you where this Gaussian is centered. Second moments tell you the shape of the Gaussian, the width and how broad is it, how squeezed is it. So second moments contain these covariances, so correlations between the different quadrature operators. And in order for the state to be physical, there's a constraint that has to be satisfied by this covariance matrix, which is has to obey this inequality here, where this matrix is called symplectic matrix, and it's a matrix that in a very compact way encodes the commutation relations. So say commutation between x and p is I h bar, px is minus I h bar, and if you go between different modes it's 0. So that's why this matrix takes this form. We put h bar to 1, and commutation relations are written in this way. So this condition is equivalent to the Robertson-Schrödinger uncertainty principle. So any covariance matrix that obeys this corresponds to some physical state on the Hilbert space level. So the state is specified by this vector and this matrix. Very good. And what we want to do now is to consider resource theories where we are limited to the set of Gaussian states and we are limited to the operations that preserve the set of Gaussian states. Now within this we have to choose whatever resource we want. So if we want to study entanglement in the context of Gaussian resource theories, then our free states will be separable Gaussian states, and free operation will be LOCC that preserve Gaussianity. Okay, so in general, for any given resource, we will define our set of free states as the intersection between the set of free states in general for that particular resource, say all separable states, and the set of Gaussian states. Now, one important thing is the set of Gaussian states by itself is a non-convex set. Because if I take two Gaussian states and I mix them together, you can actually even think about this. So this is a Gaussian and then I mix with another Gaussian, I obtain, this is like a profile of the Wigner function, I obtain something like this, which still has a positive Wigner function, but it's not a Gaussian shape anymore. So mixing two Gaussian states in general does not lead to another Gaussian state, so the set is non-convex. But we can still define this kind of hybrid set of free states as the intersection between the set of Gaussian states and the typically assumed convex set of free states in any given resource. Similarly for the operations. So the operations we will take as free operations the maximal set of free operations for any given theory that preserve Gaussianity. So you take again the intersection between this maximal set of operations sending free states into free states and overlap it with the set of Gaussian channels which map Gaussian states into Gaussian states. So this is the maximal set of operations sending this set into itself. So this is the structure we are trying to construct. So what we want to do now is we want to impose a series of natural postulates inspired by the ones that were given by Brandau and Gur in the previous work on finite dimensions, and see what happens now with this Gaussian restriction if we get some significantly different result as opposed to what they had there. And the answer is yes. Now, the postulates are the following. Some of them are really translated from the other ones, and then we have to add some extra ones which are specific to the Gaussian structure. So we assume resource theories where our set of free Gaussian states is closed under tensor product and the partial traces, permutations, that's all fine. This one is non-trivial, but we can still assume it, because if you go to our paper or if you talk with Ludovico in the red t-shirt there, he proved that the set of Gaussian states is still topologically closed with respect to trace norm, which means if I have a sequence of Gaussian states and they converge to a different state, that state is also Gaussian if this convergence is in trace norm. And in particular, this is inherited in the subsets of free Gaussian states. So we can take free Gaussian states closed in the topology of the trace norm. What are the extra postulates we're going to put here? One is this one. This one appears everywhere whenever you do continuous variables quantum information theory. So these placements, the first moments, are completely irrelevant. Because as I said, all the information about, say, the entropy, the correlations, any resource power of the state is encoded in the second moments. Wherever this Gaussian is centered, doesn't really matter. So I can take my free states and move them around freely in phase space by means of local unitaries, local displacement operations. This should not give me from a free state something which is non-free. So the set of free states should be invariant under displacements, and this we can actually put it as a postulate. And the final bit is, you remember in Brandon-Gurt they require convexity of free states. Here we can't, because Gaussian states are non-convex, but we can define a notion of convexity specialized to this. So we say that this set we require to be Gaussian convex. What does it mean, Gaussian convex? If I have a collection of free Gaussian states in my set, and then I take a convex combination of these, and the output that I obtain is Gaussian, then has to be free. So convex combinations of Gaussian free states, when they are Gaussian, they have to be free as well. When they are non-Gaussian, nobody cares, they are out. Okay, so this is the requirement that we put. Why we do this? Because let's see what these two imply. The other ones are standard. So invariant under displacement tells us that, now remember, before I was defining the state in terms of a D and a V. Now I can forget about the D. So everything that matters now is just a covariance matrix. So instead of representing things in an infinite dimensional Hilbert space, I just move into the space of matrices, which are 2n by 2n real matrices, where n is the number of modes of my system. So instead of that, then I have a simple structure where I divide the space of matrices into matrices corresponding to free states, and this will be the subset V, covariance matrices of free Gaussian states, and then the other ones. And then if I put these two things together, this I get a very important property. So that's why I need this Gaussian convexity. The property is that the set of free covariance matrices is so-called upward closed. Upward closed means if I have a covariance matrix which is free, any other covariance matrix which is larger than this one in matrix terms is also free. And why is this interesting and also intuitive physically? Because having larger covariance matrices means having something more noisy. And you can think of, so if you think of all these oscillators and think about the fact you can do normal mode decomposition of them. So you look at the normal modes. Pure states, they have all normal modes in the vacuum. Any other states, they have all normal modes which are in some thermal states at higher temperature. So having something more thermalized means something more noisy. Pure states, they are the minimal covariance matrices. Mixed states, they are larger in this sense. Okay, so this corresponds to the fact that somehow adding noise should not, to a free state should keep it free. That's the idea. And curiously, I draw the picture in this way, but curiously these two things are not enough for me to conclude that the set of quantum covariance matrices, free covariance matrices, is actually convex. I need an extra bit. We are not going to assume this extra bit, but it turns out to be the case for all the examples we have. But this extra bit is, if my set of free Gaussian states is also closed under another operation that is cheap to do in the lab and that normally doesn't create anything, which is mixing states with each other by means of 50-50 beam splitters. If I do that, and I include these two postulates and this extra bit of information, then it turns out that even though the sets of states in the Hilbert space are all messy, within the covariance matrices, the set of free covariance matrices is actually convex. As I said, we're not going to assume this, because what we really need is this upward close, that you mix more and then you get free states into free states. The idea is similar to convexity anyway, so discarding information shouldn't give you resource. Okay, so now we are constructing a class of resource theories which are all within the Gaussian world of states and operations, and that obey a certain series of postulates. We will see what will be the conclusion of that, but first of all, let's give some examples. First example is entanglement. Say I have two modes or more modes, bipartite system in a Gaussian state. Separability can be characterized very simply in this case. Gaussian state is, look, I do everything at the level of covariance matrices, because first moments are irrelevant. They are separable if when there exist two local covariance matrices. This means they are physical in their own respect for A and B, such that your original covariance matrix is greater or equal than the direct sum of these. And this holds for any bipartition of Gaussian state. And free operations are Gaussian LOCC. And this also can be characterized in terms of matrices which transform covariance matrices. Another example is steering from A to B. As I said, for steering, you don't make any assumption on one of the sides, and this is particularly transparent in the condition here, because we are saying the states are unsteerable by Gaussian measurements when, see what happens, when they still are physical. This is similar to the condition for the state being physical, but you're only putting the commutation relations on the B side, you're not assuming anything on the A side, so you don't have to assume quantum mechanics on A. If the state is compatible with this, then you can't verify steering. If it violates this, then state can be steered from A to B by means of Gaussian measurements. And free operations are Gaussian one-way losses. So there's been a study about this for different reasons with lots of experiments and so on. All these resources I'm mentioning, they satisfy those postulates. So they are good examples, and actually we couldn't find any relevant example that violates them, apart from one, which I can tell you. Another simple resource is this non-classicality, as I said. So in the Gaussian sense, it just means squeezing. Okay, so if a state is thermal or the vacuum, then it's not squeezed. Otherwise, if the variance in one of the quadrature is different from the variance in the other quadrature, you typically have squeezing. And so in this case, the free states are just states that satisfy this simple condition, covariance matrix greater or equal than the identity. And free operations are operations that are called passive operations. So you can append free classical states or other states which are from the set, and then do passive operations, so optical operations that preserve the energy, and do discarding. So this is another simple resource theory for a single system. The other ones are for bipartite. Now, in all of this, we can quantify the amount of resource by different ways. So there are lots of entanglement monotones calculated for Gaussian states, steering measures, non-classicality squeezing measures, but we want to come up with what's one particular new monotone that is universal for these theories, and is constructed ad hoc because it allows us to prove general theorem on the state transformation there. So what is this monotone? I define it in this way. It's, if you think about it, looking at it, it reminds me at least of the concept of robustness, even though it's defined a bit different. So for a given covariance matrix, this monotone is the minimum factor such that, you know, enlarging your covariance matrix by this factor makes it free. So it's a bit similar to this idea of robustness, where you have to look at the minimum tolerance of a mixture with some other state until your state becomes free. This is again a sort of minimum added noise until the state becomes free. It's very simple. And now what happens here? This has interesting properties. One is, okay, it's faithful, but be careful here. Faithful means on the free states it's equal to 1. If you want it equal to 0, put some log. It doesn't matter. So it's greater or equal than 1 for any state. It's equal to 1 if and only if the state is free. It's continuous. Of course, it's a monotone. You have to prove. So for every resource theory of that sort, you consider the Gaussian, the maximal set of free Gaussian operations. This is a monotone. But this is the most interesting property. Normally, we like measures which are actually additive on tensor product states. In this case, this is completely the opposite. So if I have a tensor product state, which at the level of covariance matrix translates as a direct sum, then this measure is the maximum between the individual measures on each of them. And so if I have n copies of the same state, the monotone is equal to the single copy one. Instead of scaling as n, doesn't scale at all. So I don't know why we call this tensorization property, but anyway, this is a very interesting property. We didn't invent it. It was already studied in the case of entanglement. Quantity with this sort was already studied in the case of entanglement in these old papers. But now we show that we can define it for every resource theory that obeys those postulates, and it always has these properties here. Okay, then I can give you an extra piece of information about this measure, which is if your set of states, this we have to add extra, if your set of states, like let's say membership to the set of free covariance matrices, if this can be decided by a finite set of linear matrix inequalities, then the whole thing can be characterized as an SDP. So your resource theory is easy to evaluate. So characterizing a state being free or non-free is an SDP, and quantifying the monotone as defined before is an SDP. And in particular, we can write it in a kind of general template. So this kappa is the max between 1 and kappa prime, where this kappa prime is, you have to optimize over some number and some matrices. These I left bipartite in general, but of course it simplifies in the case of single partite resource, such that, okay, lambda times your state is greater or equal than some functions of this auxiliary covariance matrices plus some other things with some extra linear constraints. This is a kind of general form that encompasses all the resources that I had before. So in particular, I'll show you the table with the special cases, and of course, if you do look at the dual of this, then you obtain resource witnesses, and these are very useful in the lab in order to certify, even quantitatively, the amount of, so the presence and the amount of, give bounds on the amount of resources for each of these particular states, and they can all be evaluated efficiently. So in this case, this is a summary of the ones I mentioned, so separability, so resources entanglement. There's a simplified way of checking entanglement that we studied with Ludovico in a different paper, where instead of optimizing over two local matrices, you have to optimize only on one side. So it makes it even easier numerically, especially if one block is much bigger than the other, you do it on the small one. Negativity of partial transpose, steering, non-classicality, all of these can be rewritten in this way. Your monotone is an SDP for all of them with specific, I don't have to care about the specific things here, but this you can check in the paper if you want. Okay, so what do we want to do with this? So we want to obtain a general result. Randall said resource theories are reversible, so I can do state transformation back and forth, losing nothing. If you impose the Gaussian restriction with a very similar structure, you get a completely different result. Actually, you can't distill anything at all. And the theorem is easy to formulate. First of all, let's say it in Word. If I have any resource theory defined on Gaussian states and operations, which satisfies those postulates that we had, 0 to 5, it is impossible to convert even infinitely many copies of a Gaussian state into even a single copy of another Gaussian state which has a higher amount of resource than the initial one, as quantified by this monotone here. So theorem goes like this. If I have two states with respective covariance matrices V and W, and kappa of V is smaller than kappa of W, there does not exist a sequence of Gaussian free operations Wn, a sequence of covariance matrices Wn such that I can convert n copies of my V into this Wn, and the limit of this Wn is actually the state I want. Now, I think we can prove this very, very easily. Actually, I don't even have to write. So, actually I can, because it's one or two lines. So you prove by contradiction. Suppose that there exists this set of free operations, okay? So this means, so suppose that they exist. This Wn. So what we do from here to here. If we do from here to here by free operations, because this kappa is a monotone, it cannot increase, right? So we have that the kappa of V copy n is greater or equal than the kappa of Wn for every n. But then you use this property of this guy that the kappa of the tensor product is actually the kappa of a single copy. So kappa of V here is greater or equal than kappa of Wn for every n. And then you take the limit, and because this kappa is also continuous, this guy in the limit converges to kappa of W. And so you have that kappa of V is greater or equal than kappa of W, which contradicts your assumption. So that's it. So you use properties of this to be a monotone, to be continuous, and to be with this tensorization property. And so this means that even beyond I.I.D, so if, of course, if I have a single copy of a Gaussian state, I can't do it in another single copy of a more resourceful Gaussian state by Gaussian free operation. But even if I have infinitely many in the beginning, I can't get any single copy out of just something slightly better. Okay, so this is a very powerful result that tells us that in general, the power of Gaussian resources is extremely limited. Even if you start with a structure very similar to the other case, here you get resources which are completely reversed. So applications apply to all those specific cases before. There was a famous result in those years about entanglement. So distilling Gaussian states by Gaussian operation is impossible. This was done specifically with techniques a bit similar to this, but it was with LOCC. Now we know that we cannot even distill by using larger sets of operations, such as say PPT preserving operations, which are Gaussian, because this holds for the maximal set. And again, now we learn that you can't distill Gaussian steering by Gaussian one-way LOCC, you can't distill squeezing by passive operations, and so on and so forth. So if I have to compare this result to to the other ones and kind of summarize and give a little bit of outlook, I would say, so remembering what I said, so in general resource theories, you want to go from one state to the other by means of free operations. You can do the single shot as we like here in beyond I.I.D. You can do it in the asymptotic limit. And for some resources, you have some target, golden unit, say the maximally entangled state or the maximally resourceful state, and you want to convert back and forth from it. So if you start from maximally resourceful state and then you create more copies of just one less resourceful state, this is called a dilution. And the quantifier in the asymptotic limit is usually the resource cost. On the other hand, if you start from a state and then many copies and then you compress it and obtain less copies of a better state, then this is the distillation. What they showed in Brandau and Gur under their assumptions is that these two processes have an equivalent, they can be performed reversibly. Okay, so the rate is the same in the asymptotic limit. So theories which are with this set of assumptions are asymptotically completely reversible. What we found here is that if you try to apply very similar assumptions, but you make the restriction that your states are Gaussian, your operations preserve Gaussianity, then this thing here is completely impossible. So you can't increase the resource content, or in particular, the distillation is forbidden. So if you want to use the terminology that we are familiar with, every resource is a bound resource within Gaussian states and operations if they satisfy our series of very reasonable postulates. And so you always have to invest some cost in diluting Gaussian resources to create more copies of your state, but you can't get anything back, even if you have infinitely many to start with. That's the thing. Okay, so this is maybe not surprising to many people, but it was nice in the end to settle this in general, because we had several examples of no-goes for Gaussian states and operation. Now we have a general framework to that gives us reasonable assumptions for the theories, but in the end allows us to conclude that seriously you have this very fundamental limitation. This doesn't mean that they're useless, so you don't always have to distill resources. You can still perform, say, teleportation, metrology, cryptography. Everything is done with Gaussian state and operations, apart from quantum computing that requires some element of non-Gaussianity. But at the level of resource theories, you have this fundamental limitation. Okay, so these are maximal irreversible in this case. So now if I want to summarize, this finally settles this question that many of us have had, or many other people didn't have and didn't care, but still we're happy about it. So there are some questions that we would like to tackle. I mentioned just a few of them. So one is, so far I gave lots of examples, and all these examples, they are characterized by SDP. But it didn't follow directly from the theory, so we put some postulates out, and then we noticed that all the examples we have are actually also SDP. So do we have to add any extra postulate in order to imply that every Gaussian resource then becomes an SDP? Or it just follows from our postulate, or maybe not. So maybe there exist some other resources which are compatible with our postulate, but they are not SDP. So there will be something in the Gaussian world that is not easy to compute, which is surprising, but maybe we can look into this. Second thing is look at analogs for finite dimension. So there's a lot of analogy between set of Gaussian states in infinite dimensions and set of stabilizer states in finite dimension, and Clifford operations as opposed to Gaussian channels. Some results are analogous in information theory, inequalities, and so on. Say even the so-called Hudson's theorem, the fact that the only pure states in continuous variable with the positive Wigner function are Gaussian. Similarly, there's the version for discrete Wigner functions that deal with the stabilizer state. But I don't know. So I think we have some preliminary results that we can't establish a similar no-go within, say, a resource theoretic approach to stabilizer states. Maybe we have to have some extra assumptions in order to do that. Maybe there is more freedom here. And this connects to resources of contextuality and magic and so on. And then if you want to overcome the no-go, then of course you have different opportunities. One obvious case is you resort to non-Gaussian operations. They give you infinitely more power, and then of course you can distill stuff. But if you want to stay within the Gaussian, then what you can do, you have to bring in some help. So if you stay within the Gaussian, then you have an assistant party, then you can do something. So I have the slide here, but I don't think I want to discuss it too much because the time is up. So if I have, just quickly, so if I have my system, I want to concentrate resource on this system, but it's correlated with an ancilla, And then my paradigm is now, here I can only apply free Gaussian operations. Here I can apply any Gaussian operation. Still everything is Gaussian. This is all Gaussian, free Gaussian, any Gaussian, classical communication, one way or two way. And then I want to concentrate more resource here. If I don't have this assistance, I can't. But with the assistance, we can. And you can define the resource of assistance, which is like entanglement of assistance or coherence of assistance. This has been studied in specific cases. You can define it all within the Gaussian context. Let's not talk about the formula. And then you have several results. This is work in progress we have. For instance, the easiest you can look at is how to distill squeezing with assistance. If you have only squeezing without assistance, this is given by the inverse of the minimum eigenvalue of covariance matrix. If you have assistance, you can distill more. It's given by the maximum eigenvalue of covariance matrix. So the more mixed your state is, the more you can extract extra squeezing by having the assistance of another party who measures and then communicates results, and then you get something more. And this is all Gaussian. Of course, here is restricted by free, here is non-free. But within all Gaussian with assistance, then you can break this normal. And this is something we are working on, will appear somewhere else. So far I want to thank you. Then I want to emphasize that this work has been done with several people here. So Ludovico is here, Bartosz is here. Ludovico is not in our picture, unfortunately. We have to retake it. Chinwan is here as well. Rosanna is here. She's writing up the thesis at home. Andreas is also here, and it's me. And they didn't like it because it was not surprising enough. So thanks a lot.
Questions? So if you wanted to consider non-Gaussian operations, do you have a candidate? What would be for you the natural first, easier?
I think there is a nice family which is so okay, it's a jungle, right? So you can take whatever. One of the typical non-Gaussian operations that you bring in the picture to break this is photon count. So you do some kind of non-Gaussian measurement. And this helps, say, for quantum computing, if you want to do universal one-way quantum computing, you have Gaussian cluster states, but then you have to do some photon counting at some point. So you have to, maybe you can take all Gaussian channels supplemented by photon counting only. This already helps a lot. For instance, it helps already for squeezing distillation. It gives better results than the Gaussian assisted case. Other possibility is to consider some suitably variation of Gaussian channels where you can always dilate a channel with having a unitary on a larger system, and then you discard, right? So we can have a Gaussian unitary, but the other input you put some non-Gaussian states, say some Fock state. And then you have a construction of a family of non-Gaussian channels that has been characterized also in terms of cross representation. So this one we could also, Andreas, Ludovico have worked on this. With this one we can try. But we can never have any general result, no? Because we can, I don't know. Maybe it would be nice to characterize, say, edges around the Gaussian such that maybe you have still some limitations, and then at some point you break. But I don't know, maybe we can. We have also to be driven by what people can do in the lab. I can invent some complicated operation, but then they can't do it.
And would catalysts play any role in going beyond this no-go theorem?
I think we show that they don't work, right? Catalysts don't work, right? Catalysts
don't seem to work.
So far, we don't have a final answer.
In new states, we know they don't work.
Yes. This was studied before. In mixed states, we don't have a final answer, but our feeling is that no. But this is still to be said.
And this catalyst is also Gaussian?
Yeah, of course, everything Gaussian. Yeah. But this kind of assistance, not catalytic, then we have.
Okay, so if there are no more questions, let's thank the speaker again.